And here we go. So section 4.7, again, all about optimization. Okay, and when we optimize something, we're trying to maximize or minimize it. So we might want to maximize profit, minimize cost, maximize the usage of a certain material or something like that. And in most of these problems, it comes down to doing what an engineer does. So engineering a solution to a problem, we need to be aware of a couple of things. First of all, what's the objective? What are we trying to accomplish? Okay, and the second thing is, what are the constraints? Okay, what are the conditions that have to be met? Okay, what criteria has to apply to this situation? So in the problem that we had there, we had a certain size piece of paper, and we were trying to fold it into a box, and we were trying to maximize volume. So the objective was to maximize volume. Okay, the constraints were we had a certain size piece of paper, and we had to be able to cut out corners and fold it up and all that sort of stuff. Okay, so let's talk about just kind of a classic algebra and calculus problem. So I think this is in your textbook or one very similar to it. They call this rancher's dilemma. So a rancher has 400 feet of fence to construct a rectangular corral. One side of the corral will be formed by a barn that requires no fencing. Okay, so we're going to have there's a very large barn. We're going to put the fence up against there, and we're going to corral the animals against the barn. It says 3 exterior fences and 2 interior fences perpendicular to the barn partition the corral into 3 rectangular regions. Okay, what dimensions of the corral will maximize the enclosed area, and what is the area of the corral? So we've got this barn sitting right here, and then we're going to take a fence, and it's going to come out here, go over here, and back here. It's going to be a rectangular corral. And then it says we've got some fences, 2 fences that we're going to put on the inside that are going to be perpendicular to it. It doesn't say where they are, and if you think about it for a second, it doesn't really matter. Because the overall area, no matter how we divide it up inside, no matter how we partition it inside, it's still going to be the same size corral overall. Okay? It's just how much we leave for the chickens, the pigs, and the goats and stuff like that. Okay? So I think the easiest way to start off with a problem like this is we're used to declaring variables and saying, I don't know how big this quantity is, so I'm going to use an x to represent it. Okay? So if you'll notice, if I choose x to be this one right here, I've got 3 other sides that I know what I can use to describe those. So this is going to be an x, and that's going to be an x, and that's going to be an x. We like working with x's, so the more of them are labeled with x, the better off we are. Okay? Do we know how long this is? Peter says yes. Okay, let's go with not exactly then. If we don't know what it is, let's use y to represent it. It will be. Hang on just a second. Okay? Okay, now if you're thinking ahead, you can come up with an expression for this, but here's the idea. Everybody knows the area of this rectangle right here. If it's going to be like this, if it's y units wide and x units tall, what's the area? X times y. Okay? But we don't work with functions with 2 variables. So what we don't like about this is there are 2 variables. So when people were saying, well, yeah, we can come up with something that represents that, this is the idea. We're going to get rid of one of these variables. Now remember how we said we like working with x? Let's keep the x around. Let's get rid of what y is, or let's write an expression for y in terms of x. So one of the constraints in this problem is we've got only 400 feet of fence. So if I take all these lengths of fence and I add them together, so I take those 4 x's and the y and add them all together, I've got 400. And this is what these people are saying, yeah, I know how long that is. This is what they're thinking. They're saying if the whole fence is 400 feet long, if you add up all the fencing and it's 400 feet long, and I used x here, and x here, I've used 4 x's, had 400 altogether. So whatever's left of that, or in other words, y would equal 400 minus 4x, that's got to be what's left. So this quantity right here would be 400 minus 4x. Now, if you don't need to write down this equation, or don't need to write down x plus x plus x plus x plus y equals 400, and then go from there, that's totally fine. And then the point here is what we're writing down is a function of x. The area of this corral is going to be x times 400 minus 4x. And once I get it to here, most of the time that's the difficult part of the problem. We're still going to have some calculus to do. And depending on how nice or how ugly the answers are, maybe it's not too bad. Okay? So I want to take this and I want to write it in a format that's easy to do calculus on. So I'm going to write 400x minus 4x squared. And then I want to maximize this right here. That's what I want to do. I want to take that and I want to maximize it. So if you think about the difference between this problems and the ones that we've been doing so far in this chapter, we had to come up with the function that we're going to maximize, and then we're going to maximize it. So from here on out, we ought to kind of be on autopilot. Now, we ought to at least talk about the real-world domain for this problem. Okay, what's the smallest number we could choose for x? Okay, really close to 0. Okay, we probably wouldn't do this. We wouldn't be in the ranching business very long if we did this. Okay, I'll use this for the barn. If I came out just a little bit and went like that, okay, I'd need a really long barn. The barn itself would have to be 400 feet long, because I'm hardly going out from the barn at all, and then I'm running right along here and then heading right back to the barn. And the animals wouldn't be very happy. Okay? Okay? There'd really be no space there, right? Okay? So do we need to check to see if that end point, really is that an end point that we need to check and see if that's the maximum? Okay? No, it's not. What's the largest x could be? Really close to 100. Okay? So the real world domain for this is 100, and that would look like this. Coming out 100 feet, or just shy of 100 feet, going over a little bit and coming back, and then having 2 fences in the middle there. Not happy animals. Okay? So the real world domain is from 0 to 100, but doesn't include either one of them. Okay? If we use 0, we don't have a rectangle. If I used 100, I'd have 4 100-foot fences sitting right next to each other. Okay? No area whatsoever for the animals. Okay? So the only place I'm going to find a maximum is where the derivative equals 0 or where it doesn't exist, and look how easy this derivative is. It's just 400 minus 8x. It exists everywhere, and it equals 0 when? When x is equal to 50. Move the 8x over, divide both sides by 8, you get x equals 50, right? Okay, so it says, what dimensions will enclose the maximum area? Well, if x is 50, then here's what we've got. I've got this one right here being 50, this one's 50, this one's 50, and this one's 50. How long is this one over here? This would be 400 minus 4 times 50, so that's going to be 400 minus 200, so that's 200. So the dimensions are 50 by 200 feet. Those are the dimensions. And what is the max area? We just multiply these together, right? So it's going to be 10,000 square feet. Now, I can get that by multiplying the dimensions together. I can also get it by taking this x value right here and plugging it into the function. Because if I figure out what a of 50 is, this would be 50. This would be 400 minus 4 times 50. I still end up with 50 times 200, which is that answer right there. Okay? So I found the x coordinate of the maximum. I plug it in to find the y coordinate of the maximum, or in this case, what the actual maximum area is. Okay, any questions? Okay, let's take a look at another one. And let's talk about just some general guidelines. In the textbook they go through, I'm not sure this is exactly what the textbook has, but usually we can break this down into 3 steps. So here's what we do first. Read and understand the problem. Make sure you know what it's talking about. Okay? Identify variables. Identify things that you're not quite sure of, and the constraints of the problem. In the last problem, we can make a gigantic corral to put these animals in. We have tons of fencing. If I have an unlimited amount of fencing, I can make any size I want. Okay, the constraint there was that it was 400. We want to draw a diagram if possible. The previous problem was about a rectangle, so we drew a rectangular corral. Okay, that can be really helpful in figuring out the geometry. And you want to ask yourself questions like this. What's changing in the problem? Okay? What do I have control of? Okay, when we drew the different pictures of, well, I could draw it really long like this or really skinny like this. Okay, that's what we're talking about. How can I change the dimensions of this? Okay, what quantities are given? Like they gave us 400. They told us it had to be a rectangular shape. Okay, and what is limiting those quantities? In that one, we had 400 feet of fence. Identify the type of function that needs to be optimized. In the previous problem, it was an area function. Okay? If we want to maximize the area, we've got to come up with an area function. Okay? Write the function in terms of the variables and the constraints of the problem. So we declared the variable to be x, and we also had a y, but we got rid of that y so we could write it in terms of x. Okay? If necessary, it says use constraints to eliminate all but one of the variables. That's what we did there. Okay? We didn't like having the two variables x and y, so we wrote y in terms of x. Okay? And then usually it's a good idea, if you're going to get to choose variables that remind you what you're looking for. That's why we called it the function a rather than the function f. Okay, a reminds us that we're trying to maximize the area. Okay, and then use calculus to optimize the function. Be sure to think about what the real world domain is for the problem. Okay, that's why we didn't use 0 and we didn't use 100. There's no way we're going to maximize the area if that was what x was. Okay. But there are times where you'd want to check the endpoints, and I think we'll run into those in just a second. Okay? All right, so let's take a look at this problem. This one's slightly more challenging, but it's still kind of a geometry question. It says, you've been asked to design a 1-liter can shaped like a right circular cylinder. What dimensions will minimize the material used to construct the can? So, 1-liter can shaped like a right circular cylinder. Those are some constraints. They've given us what the volume has to be. It has to contain 1 liter. Okay, and they've told us what shape it has to be. So let's draw a picture of what this looks like. The volume has to be 1 liter. Okay, what's the volume of a right circular cylinder? It does have a pi in it. What is it? Okay, pi r squared h. Remember this from the related rates section? Okay. We've got a couple different variables, so we've got some work to do here. Okay. Let's see. It also has to be 1 liter. That volume has to be 1 liter. This has got to be equal to 1 liter. That volume has to be equal to 1 liter. Let's see, at this point, let's think about this for a second. Are we trying to maximize the volume? No. Minimize the volume? We're trying to minimize the amount of material used. So I don't even have the right function on here to work with this to minimize something. I'm trying to minimize the material, so let's think about how we'd figure out what the material is here. How much material does it take to make a can, or how do you figure out the material used to make a can? Okay, area of the top and bottom. Okay, so if I were to take this and I were to say, cut the top off, I'd have a circle, right? If I cut the bottom off, I've got a circle. And then if I take the side and cut it vertically and then lay the whole thing out, wouldn't the side be made of a rectangle and the top and bottom are just circles? Yeah. Okay, so this right here is just a circle. What's the formula for the area of a circle? Pi r squared. That one's pi r squared and that one's pi r squared. Okay? Now, we had a radius here and we had a height here. That's how we figure out what the volume is. That height would be the same. How do I figure out how far it is from here to here? The length of that rectangle, if you want to talk about it that way. Circumference of the circle. And the circumference of a circle is 2 pi r. So what we're really trying to minimize here is we're trying to minimize the surface area. So I'm going to write S for surface area. And the surface area is going to equal 2 of these circles. So 2 pi r squared. And 1 of those rectangles. And that rectangle is 2 pi r h. There's the length, there's the height. There's the base. There's the width, however you want to talk about it. Good there? Okay, so we want to minimize this right here. What's the problem with this? Two variables. We really don't like working with that many variables, so we've got to get rid of them. Okay, now we've talked about this right here, but we haven't used this constraint. We've got to hold 1 liter. The volume has to be 1 liter. Okay, now, can I just say 1 equals pi r squared h and start solving? No, because a liter isn't a measurement of lengths and widths and heights and all that sort of stuff, radiuses and heights. Okay, so from your science days, the cool thing about the metric system is if I've got a liter is defined in terms of, well, let's do milliliters. What's a milliliter? A centimeter cubed. So a liter is 1,000 milliliters. So 1 liter is 1,000 cubic centimeters. So we're not going to set this equal to 1. We're going to set it equal to 1,000 because that's going to be in units of linear measurement. And then what do I do with this? How does that help me? Okay, let's solve this for h. That's the variable we want to get rid of. Okay, so if I solve this for h, I get h equals 1,000 over pi r squared. And now we're going to have a function of r. So I'm going to write the surface area as a function of r. This is 2 pi r squared. This is 2 pi r. And then h is 1,000 over pi r squared. So this is going to be 2 pi r squared. I'm going to cancel the pi with the pi and one of those r's with one of those r's. So this is going to be 2,000 over plain old r. Okay, that should be the hardest part of the problem because this is what we're going to minimize. Okay, let's think for just a second. If it needs to contain 1 liter, what's the smallest r can be? Could r be 0? It couldn't. Okay, could it be just a little bit bigger than 0? It could. Think about the shape of the can if r was a really tiny number. It certainly can't be negative. Can't be 0. We wouldn't contain anything. Okay. Okay, it's going to be a tiny thing like this, and it's going to be really tall. Okay? Okay, so we're not going to use, the circles aren't going to be very big, but we're going to have a huge amount of surface area because the can has to be really, really tall to contain 1 liter. Does that make sense? Okay, now, how big can the radius be? Think about that for just a second. If you've got to contain a liter of, we'll call it liquid, how big could the radius be? Well, let's think about it this way. Do we really care how big it is, or do we just want to know, gosh, there's no limit to how big it could be? Because if I made this really big, put a top and a bottom circle on this, okay, in order to contain a liter of liquid, it's going to be gigantic. It's going to spread out. It's not going to be very tall. Okay? So the bigger I make the radius, the smaller the height has to be. The smaller I make the radius, the bigger the height has to be. So we certainly don't include 0, but theoretically, you could make that as big a radius as you want. You just have to have it really, really tiny. Okay? Yeah, if we let that go to, if we let the radius go to infinity, the height would go to 0. Okay. So do we need to worry about endpoints here? Yeah. Don't need to worry about endpoints, okay? Crazy idea to do either one of those, okay? So that means the max or the min is going to occur where the derivative equals 0 or where it doesn't exist, okay? So let's go ahead and find the derivative. So S prime is, this is going to be 4 pi r. This is going to be You want to think of that as a negative exponent, or however you want to differentiate that. This is going to be negative 2,000 over r squared. So where does 4 pi r minus 2,000 over r squared, where does this not exist? At r equals 0. Do we need to check that? We don't, so we're not going to worry about that at all. So really, we've narrowed this down to the only place this could possibly have a minimum. So we use the minimum amount of surface area possible, the minimum amount of material, is where the derivative equals 0. So when does 4 pi r, minus 2,000 over r squared, where does that equal 0? So let's go ahead and solve that. I'm going to move the negative one to the other side. So I'm going to, Well, let's see. What would be the easiest way to solve this? No, let's leave it like this. Let's see. How do you solve an equation like this? Could get a common denominator. Let's see. May have been a while since you took 1010, but I know you've used this skill since then. If you've got to solve an equation with a fraction in it, do you have to work with fractions if you don't want to? Yeah, why not multiply everything by r squared? This is going to give us a 4 pi r cubed. This is cool. This is just a minus 2,000 equals 0. Now I can start solving this, okay? So this is going to be 4 pi r cubed equals 2,000. So that means r cubed is equal to, 2,000 over 4 pi. So that means r is equal to the cube root of 2,000 over 4 pi. Okay, so if you would throw that into your calculator, let's get a decimal approximation for that. What do we got? 5.41. Okay, so 5.41 something or other, and that's in centimeters. No, that's just the radius. That's just what the radius is. The radius is 5.41 centimeters. What do you mean the cube? Yeah, if this is cubic centimeters, we're taking the cube root, so that would make it just centimeters. Good there? Okay, so that's what the radius is. How would you figure out what the height is? Plug it into this right here. Okay, so the height would be 1,000 over pi times the radius is 5.41, and I would recommend keeping that decimal stored in your calculator. If you type that into your calculator, what do you get? It's kind of an interesting result. Is it 10.82? So 10.82, 10.83. What's kind of unique about the two of those? The height is twice as big as the radius, or if you were to think about the shape of this can, it would be 10.82 in diameter and 10.82 tall. So if you looked at it in cross-section, it would kind of look like a square. Squares are pretty darn efficient shapes. Now, if you think about the grocery aisles and where the cans are, do we normally see cans shaped like that? No. We normally don't. Okay? I think there's one thing that's in a can shaped like that, those Vienna sausages. I don't know if anybody even eats those. I think the same ones are on the shelf today as were on the shelf when I was a kid. Okay? Those are shaped like that, but everything else is a little taller than it is wide. Okay? It might have to do with maybe the side walls are thinner or thicker than the ones on the top and bottom, or vice versa. Okay, maybe they make the bottom a little thicker to stand up to, being plopped around and stuff like that. Okay, so there's probably a good reason for it. Okay, all right. Any questions there? Okay, we're going to spend Monday talking about this too. I've got this example of a drilling rig problem where we've got to get oil from here to the refinery for the minimum amount of cost. We've got a problem like this where we're going to minimize the distance. This is problem number 20 from your assignment. That's 35, and that right there is an example from, I think it's very similar to one on the textbook. So I'm going to try and get through, what do we got there? 4 problems? Okay. So I didn't pass around the sheet for 4.4 or 4.5. I'll do that on Monday. But if you take a look at the notes, make sure you're done with everything caught up. The representative problems for 4.1 through 4.4 are due today, so if you'd put those up here, and then we'll pick this up on Monday.